In this video, we are going to begin our second day of final review. So today's final review is going to focus on stuff from before chapter 14. So our goals for the videos today are just to do some practice problems from that content from before chapter 14. So that's the stuff from before midterm 2 to help us prep for the final. All right, so in this video, we are going to review series. Okay, so I want to look at one of the practice problems from the final practice problems. And it's the final practice problems part 2. So remember, there's 2 parts to the final practice problems. Part 1 was the most recent material from chapter 14. Part 2 is the older material from before midterm 2. Okay, so this is problem number 1, and I want to look at part A and part B of this question. So this is true or false problem. So first, I want you to pause the video and try this on your own for about 3 minutes. So 4, 3, 2, 1, pause the video. Pause the video for about 3 minutes to try this question on your own. Alright, so hopefully you've done that. Hopefully you paused the video for about 3 minutes to try this. If not, go ahead and do so now. That may not have been enough time to finish the question, and that's okay. I mostly want you to think about how you would begin and what the key ideas are. Alright, so let's start to talk about this together. So before I get into the question, I want to incorporate some review. So what are some key properties of series that we need to remember to tackle a question like this? Okay, so the first is, so if we have a series, so I'll just say it goes from n equals 0 to infinity with a sub n, and this series converges. So if my series converges, then the limit of the terms, so the limit as n goes to infinity of a sub n, so the limit of the terms has to be 0. Equivalently, so an equivalent way to say this is, if the limit as n goes to infinity of a sub n was not equal to 0, let me put a slash through this, was not equal to 0, then our series from n equals 0 to infinity of a sub n would diverge. This series diverges. Okay, and you might recognize this equivalent statement. So this equivalent statement we call the nth term test. This is the nth term test, which tests for divergence. If the limit of my terms, the limit of a sub n, is something that's not 0, and then my series is going to diverge. Okay, so I want you to have sort of a conceptual sense why this is true. So why? So the reason why is if the limit as n goes to infinity of a sub n is not 0, so for example, that happens in part A, where the limit of a sub n is not 0 because it's 1. So for example, let's say the limit as n goes to infinity of a sub n is 1, like it is in part A. What would that mean about the series? This would mean that the series from n equals 0 to infinity of a sub n, if I start to write out the terms, I'll get a sub 0, plugging in n equals 0, and then a sub 1 from plugging in n equals 1, plus a sub 2, and and so on and so on. So I'll put plus dot dot dot. But eventually, at the end, what I'll get is, I'll get some terms that get really close to 1. So I'm just going to write plus 1, plus 1, plus 1, and then plus dot dot dot. It keeps going like that forever. But when I write these ones, I just mean that these are really close to 1. Really close to 1. They don't have to exactly be 1, but I know the limit of a sub n is going to be 1, so eventually the terms get really, really close to 1. And once we reach that point where the terms get really, really close to 1, what I'm doing is I'm basically adding 1 plus 1 plus 1 an infinite number of times. And that is definitely infinity. Okay, because I'm adding up an infinite number of ones, essentially. So before that point, we have a finite number of terms. So this is a finite number of terms here in the front. So whatever they are, whatever these numbers are in the beginning, no matter how big, because I'm just adding a finite number of terms, this would be something that's finite. So overall, I have something finite in the front, and then from adding all the ones kind of at the end, I get an infinite thing. So overall, infinity plus a finite number is infinity. The infinity dominates. Okay, so I'm going to put this in a little bubble here. This is kind of the conceptual reason why the nth term test works. Okay, so what's our conclusion now for our problem? So therefore, in part A, since the limit as n goes to infinity of a sub n equals 1, and that's not equal to 0, that means the series from n equals 0 to infinity of a sub n diverges. So a series diverges by the nth term test. By the nth term test. So as a result, so what was the problem saying? Was it saying it should diverge? Yeah, the problem was saying it diverges. Series diverges. So that means we just showed that this is true. We just showed this is true, and this was our entire justification. So I'll even box the entire justification just so that it stands out a little bit. All right. So I want to review a little bit more about series before we take on part B. But before I do that, I'm going to just highlight this stuff. This is a key property of series that I definitely want us to know. Okay, and I'll highlight this one as well. The nth term test, the equivalent way of saying it, nth term test. All right. Okay, so now we talked a little bit here about, well, so the nth term test tells us, well, what happens if the limit of a sub n is not 0? Then the series diverges. Well, what if the limit of a sub n is 0? So that's what I want to talk about next. All right, so I'll put a bullet point next to this one as well. So if the limit as n goes to infinity of a sub n equals 0, then the series from 0 to infinity of a sub n. Before I fill out and say what this is, pause the video just for 30 seconds and see if you can answer this. Will it converge? Will it diverge? Do I not know? So 4, 3, 2, 1. Pause that video for just 30 seconds and see if you can fill the rest of this out. Converge, diverge, what is it going to do? All right, so hopefully you did that. Hopefully you paused it for about 30 seconds to try this. So this may or may not converge. May or may not. May or may not converge. So the trap is to say, oh, the limit of a sub n being 0, that's kind of the opposite of what we saw before. So shouldn't this converge? Unfortunately, it's not quite that simple. There are situations where the limit of a sub n equals 0 and the series converges, but there are also examples where the limit of a sub n is 0, but the series diverges. And we've seen some examples before. So what are some examples? Okay, so I'm going to give 2 examples. Okay, so we've actually seen a bunch of series like this that converge. Maybe the simplest type of example is a geometric series. So let's say I had from 0 to infinity, and I had 1/2 to the n. I'm trying to pick something where the r value is such that it'll converge. Okay, so in this example, if I take the limit as n goes to infinity of a sub n, so a sub n is 1/2 to the n power. Well, when I take this limit, it's going to be 1/2 times 1/2 times 1/2 times 1/2. And that keeps getting smaller and smaller and smaller. So this limit is 0. And this is a geometric series which converges. So this geometric series converges. So this is geometric, and the reason why it converges is if I look at the absolute value of r is 1/2. So the absolute value of r is still 1/2, and that's less than 1. So the absolute value of r for a geometric series needs to be less than 1 for it to converge. And in this problem, in this example, that's the case. Okay, so what's an example of a series where the limit of a sub n is 0, but it diverges? So the classic example, so from 1 to infinity, of 1 over n. So remember, this is called the harmonic series. Harmonic series, which diverges. We've actually proven this before when we talked about series. It diverges even though the limit as n goes to infinity of a sub n equals 0. Okay, so you might be wondering, wait, if the limit of a sub n is 0, if I use this argument that we set up here, and up here we said if the limit of a sub n was 1, kind of at the end, eventually in my series, I'm just adding terms that are really close to 1 together. So I'm essentially adding 1 plus 1 plus 1 forever, once I get to a certain point. Well, if the limit of a sub n is 0, like it is for the harmonic series, in fact, I should write 1, let's just write the formula here, 1 over n. Then following this argument, wouldn't I eventually just be adding sort of 0 plus 0 plus 0 plus 0? And the answer is, yeah, sort of. But it's important to remember that these numbers up here, they weren't exactly 1. They were just really close to 1. So even if I were to write zeros instead of 1s, they wouldn't exactly be 0. They would just be really close to 0. But overall, I would still be adding a certain amount, a certain small amount. But when I'm adding an infinite number of those small amounts, it might still end up diverging. And that's what we saw with the harmonic series. We proved this before. Okay, so if I look at part B, I'm going to scroll up one more time. Part B is saying if the limit of a sub n is 0, then the series converges. Well, based off of what we just said, we just realized that if the limit of a sub n is 0, then the series might converge, but it also might not. So therefore, in part B, even though the limit as n goes to infinity of a sub n equals 0, the series from 1 to infinity of a sub n might still diverge. So I should be able to justify why with an example. So for example, we know the harmonic series has this property. So as a result, this statement is false. So this statement was saying, oh, if the limit of a sub n is 0, then the series should converge. But that's not necessarily true. The harmonic series has that property about the limit of the terms being 0, but the series diverges. Okay, so let's box this as well. All right, and that is it for this example. In the next video, we are going to do some review of parameterization.